Hi everybody. So in today's video, I'm going to be going over the ideas from lesson 9.4, which is still about finding volumes by revolution. So we're still going to be revolving things to find a volume, but this method is what's called the washer method. Our learning target for today is I can calculate the volume of a solid of revolution using a definite integral. And today we're going to focus on doing that using a new method called the washer method. Before we get started, I want to go ahead and show you a visual of what the washer method is representing because I think once you visualize it, it does make it easier to set up these problems. So if you take a look at this demonstration right here, imagine that you start with a graph that looks like this, and I ask you to revolve this graph around the y-axis. So we're rotating this graph around the y-axis. When you do that, you get a three-dimensional shape that looks like this. And if you focus on this one slice, oh my goodness, I'm so sorry. If you focus on this one slice of the shape that's sort of highlighted in gray right here, you can see that that slice is shaped like what we would call a washer, which is when you're using construction, use like washers to put things together. And the reason it's called a washer is because it's very flat and shaped like a disc, but there's actually a hole in the center. Because one of these slices is shaped like a washer, even though the outer edge and the inner edge of that washer are still shaped like circles, we can't find the area by just using a circle because that piece in the middle is missing. There's like a hole in the middle. So when we set up these problems, we're going to have to take into account that we need to subtract or remove the size of the hole that's in the middle of the washer. And that's the big idea, is that our slices now, instead of being discs, look like washers. So how are we going to do that? Well, sometimes a cross section will have a hole in the middle. There's actually going to be a gap between the center of all of our circles and the outer edge of all of our circles. When that happens, each slice is going to look like a washer, which we use in construction, or some people end up calling it, think it looks kind of like a donut. There's a hole in the middle. When we want to find these volumes, we're going to need to do that by using two different radii. The first radius, which we usually call big R, is going to be the distance from the outer edge of the slice of the ring to the axis of revolution, to the very center, which is going to be in the middle of the hole. The little r, what we usually call little r, is going to be the distance from the inner edge of the ring to the same axis of revolution, this imaginary line that we're spinning everything around. Because we need to remove the center circle from the outer circle, we're going to set up two integrals in order to solve these problems. Let's say you're doing a problem in terms of x. Then you're going to find your volume by doing the integral from a to b, where a and b are your x bounds, of pi times your big R squared dx. So in other words, the outer edge, the big R for this washer, minus the integral from a to b of pi times my little r squared dx. Now, in this case, the big R is going to be the bigger radius, and the little r is going to be the littler radius. And it's important to recognize that both of these radii need to be represented in terms of x. Because if we are rotating around the x-axis or anything else horizontal, we're going to do everything in terms of x. If we want to find the volume of a solid that was created and we need to do that in terms of y, we would do the integral from c to d, because we would be using the y values of the interval now, of pi times big R squared dy minus the integral from c to d of pi times little r squared dy. And again, we need to make sure that both of these radii are represented in terms of y. So let's take a look at a few problems. We're going to do 2 problems without a calculator, and we will do 2 problems with a calculator. For this first problem, it says, suppose the region bounded by the functions, and it looks like we've got a couple different equations here. Y equals 2 square root of x and y equals 0 is revolved around the x-axis. Now, as soon as I see that I'm revolving around the x-axis, I'm going to know that I'm doing everything in terms of x. We want to find the volume of the solid of revolution, the generated solid. So first, let's sketch those graphs. So when I want to sketch the graph of y equals 2 root x, I'm going to start by knowing that my square root graph is always in my first quadrant. Now, if I plug the number 0 into that equation, I get 0, 0. If I plug in the number 1, I get 1, 1. And if I plug in the number 4, I get the number 4. So my square root graph is going to look like this. Now, the line y equals 4 is just a horizontal line. It looks like this. And I'm going to be revolving this region that I generated. So this region bounded by those 2 graphs in the first quadrant. And I'm going to go ahead and I'm going to revolve that around the x-axis. So I'm revolving around this line. Now, when I do that, the sort of the bottom part of this solid of revolution ends up down here. I'm not sketching a very good picture. It ends up down here. And if I think about one slice, so if I imagine revolving one slice of this region right here, I'm going to end up with a slice that looks like a washer because there's going to be this hole in the middle because there's a top function and a bottom function, and it doesn't touch the axis that I'm revolving around. So in this problem, because there's a gap in the middle, because I'm revolving and I end up with a gap, there's going to be 2 radii that I need to think about. There's going to be big R, which is the distance between the outer edge of the ring and the axis of revolution. And there's going to be little r, which is the distance between the inner edge of the ring and the axis of revolution. So we've got 2 radii because there's a gap in the middle. Now, each of these slices is still shaped like a circle. So step number 1 is to realize that my area formula for a slice here is still pi r squared. It's still shaped like a circle. It's just that now I'm going to have a big circle and a little circle. Big R is going to be top minus bottom, which is going to be 4 minus 0, which is just 4. And little r is going to be, again, top minus bottom. So in this case, that would be 2 square roots of x minus 0, which is just 2 square roots of x. When I set up my volume here, so that's sort of the before I set up the volume. When I set up my volume here, my volume is going to be the integral from my beginning x value, which is 0, to my end, which is 4, and then pi times big R squared dx minus the integral from 0 to 4 of pi times little r squared, which is 2 square roots of x squared dx. Now I just need to go through the process of working out this integral without a calculator. So the first thing I'm going to do is I'm going to sort of factor out the pi, and I'll deal with it later. So if I factor out the pi, the first integral becomes the integral from 0 to 4 of 16 dx. And the second integral becomes the integral from 0 to 4, pi times the integral from 0 to 4. If I square 2 square roots of x, I get 4x dx. In order to calculate an integral, I know that I need to do the antiderivative. So I'm going to do the antiderivative of 16, which is 16x plus c from 0 to 4, minus pi times, again, I need the antiderivative, so it would be 2x squared plus c from 0 to 4. And then if I sub in the top number first, I get 64 plus c minus the bottom number is 0, so I just get c, minus pi times, if I sub in the top number first, I get 32 plus c, and the bottom number next, I get just c. So the c's all cancel, and I end up with 64 times pi is 64 pi, minus 32 times pi is 32 pi, which is just 32 pi. Okay, let's take a look at another example. So in the next example, and again, this one is no calculator. We are going to do a few calculator examples in a second. It says that we have a region bounded by y equals x cubed, x equals 0, y equals 0, and then x equals 2. And we are revolving this region around the y-axis. As soon as I see that I'm revolving around the y-axis, I know that everything is going to be in terms of y. And we want to find the volume of the solid of revolution. So I'm going to go ahead and start by sketching a graph. So on a graph, y equals 0 is the x-axis, and x equals 2 is a vertical line. And y equals x cubed looks like this. So y equals x cubed, if you plug in 0, you get 0, 1, you get 1, 2, you get 8. And it looks like this. Now again, y equals 0 is the x-axis, and x equals 2 would be a vertical line that looks like this. I'm going to go ahead and take this area right here, and I'm supposed to revolve this around the y-axis. So I'm supposed to be spinning this around the y-axis, which means that the other side of this area would be somewhere over here. Volume would be somewhere over here. If I look at one individual slice like this, I can see that there's going to be an outer edge and an inner edge, like a ring or a washer. So the big R in this problem will go from the outer edge to the center of this circle, and the little r will go from the inner edge to the center of the circle. Now my area for a circle is still pi r squared. We should always start by writing down our area formula. Big R is the distance between 2 and 0. So I'm doing right minus left, so 2 minus 0, which is just 2. And little r is the distance between y equals x cubed and 0. However, I need this to be in terms of y, so I'm going to go ahead and cube root both sides in order to get x by itself. So little r is going to be the cube root of y minus 0, which is just the cube root of y. Now, after you have your area formula and you figure out what your radii are going to be in terms of y, we're going to set up our volume. So the volume is the integral from my lowest y value, which is 0, to my highest, which is 8, pi times big R squared, which is 2, dy, minus the integral from 0 to 8 of pi times little r squared, which is the cube root of y squared dy. And now I'm going to do this integral, but in order to do this, I do need to evaluate it by hand. This is not a calculator question. Once again, the easiest way to do this is going to be to factor the pi out and sort of deal with that later. And we're going to have the integral from 0 to 8. If I simplify 2 squared is just 4 dy, minus pi times the integral from 0 to 8, and I'm going to rewrite this as y to the 2/3 power. It's going to make it easier for me to do the antiderivative. The next step is the antiderivative, so I have pi times 4y plus c, and I'm going to evaluate that between 0 and 8, minus pi times, I'm going to add 1 to this power, so I get 5/3, and then multiply by the reciprocal, and I'm going to do that from 0 to 8, which means I get pi times 32 plus c minus c, because I'm plugging in the 8 and the 0, so the c's cancel, minus pi times, if I plug in the 8, I get 96 over 5 plus c, minus, if I plug in the 0, I just get c, so the c's cancel. If I rewrite this, it's going to be 32 pi minus 96 pi over 5. In order to subtract these, I have to make a common denominator. So if I multiply by 5, this guy really becomes a 160 pi. And then if I subtract, I just get 64 pi over 5 as my final answer. All right, now that we've done two problems with no calculator where we actually had to work out the antiderivative and sub in our numbers, we can go ahead and try a couple problems with a calculator. Now, this one is a calculator allowed question. So the first thing I'm going to do is I'm going to go ahead and graph these two equations. F of x equals 3 cosine and g of x is equal to 3 times 1 minus x squared. I know that I ultimately want to, and it's trapped by the x-axis, and then I want to revolve this around the y-axis. Since I'm going to be revolving everything around the y-axis, I'm going to be doing everything in this problem in terms of y. But before I go any further, I want to go ahead and get a visual. When you do that graph, you should get something that looks like this. We've got our cosine function coming down like this, and we've got our parabola coming down like this, and we are revolving this area around the y-axis. So the other side of that area would look something like this. And if you look at one slice, each of these slices is going to have a hole in the middle, like a washer. Because of that, we need to take into account that there's a big R, which is going to be the distance between the outer edge and the center of the circle, and a little r, which is going to be the distance between the inner edge and the circle. Now, each of my slices is still shaped like a circle, so I'm going to go ahead and still use my area formula, which is pi r squared for circles. Now, remember how at the beginning we said everything here needs to be in terms of y? In order to find big R, we need to do right minus left, but that means we need to figure out what 3 cosine of x would be in terms of y. So if you imagine that y is equal to 3 cosine of x, in order to get x by itself, I would divide by 3, and then in order to undo cosine, I would do inverse cosine on both sides. Now, when I do right minus left, I'm going to end up with inverse cosine of y over 3 minus 0, which is just inverse cosine of y over 3. To get little r, I need to figure out what the equation y equals 3 parentheses 1 minus x squared would be in terms of y. So I'm going to go ahead and divide by 3 again. If I divide by 3, I just have 1 minus x squared. I'm going to go ahead and subtract, I'm going to subtract the y over 3, and I'm going to add the x squared at the same time. So I'm going to have x squared equals 1 minus y over 3. I'm just sort of switching their sides. And then I'm going to square root. I know that technically I get 2 answers for a square root, plus or minus, but in this case, since all of my parts of my graph are on the positive side of the x's, I'm going to go ahead and go with x equals positive square root of 1 minus y over 3. So if I do right minus left, I have square root of 1 minus y over 3 minus 0, which just gives me square root of 1 minus y over 3. Now that I've got my big R and my little r, I can go ahead and set up my volume equation. So my volume is going to be the integral from the lowest y value is 0, and if you graph this on your calculator, you can figure out that this highest y value is 3. We're going to do pi times big R squared, which in this problem is cosine inverse of y over 3 squared dy minus the integral from 0 to 3 pi times little r squared dy. In this case, little r is just the square root of 1 minus y over 3. And then I'm just going to use my calculator and type that in. And at the end, I should get 6.046 for my volume. The last example that we're going to do today is, again, a calculator aloud question. So the first thing I'm going to do is type in both of these equations into my calculator. I want the area bounded by f of x, which is this equation, and g of x, which is this equation. And I'm going to go ahead and I'm going to revolve that around the x-axis. If I revolve around the x-axis, then that means that I'm going to be doing everything in terms of x, which is nice because both of these equations are already in terms of x. I'm not going to need to do any rearranging. Because I can use these equations the way that they are, they're already in terms of x, I'm going to make a note that I'm typing this guy into y number 1 and this guy into y number 2. And that way I can go ahead and make sure that when I recall my variables and I make my life easier by typing this in, those are the order it goes in. If I sketch this picture, both of these are parabolas and they're both in the first quadrant. So both of these parabolas, they look like this. They meet at 1 and 5. And again, I'm taking this region enclosed by those parabolas, so the area trapped between them, and I'm revolving it around the x-axis. The bottom region, if you kind of imagine flipping this over, would look something like this. And so if you imagine one slice here being revolved, we can see that there's clearly a hole in the middle. And therefore, this is going to be a problem where we need a big R and we need a little r. So big R here would be the distance from the outer edge to the center, and little r here would be the distance from the inner edge to the center. In this case, my area formula, because these are all still circles, is area equals pi r squared. My big R in this problem is going to be top minus bottom. And in this case, that top equation is just f of x. So it's just going to be f of x minus 0, which is just f of x. My little r is going to be g of x minus 0, so top minus bottom, which is just g of x, which means when I want to set up my volume would be the integral from 1 to 5 of pi times big R squared, which is just f of x squared, dx, minus the integral from 1 to 5 of pi times g of x squared, dx. And if I go ahead and type all of that in on my calculator, I should get 100.530 for my volume. All right, that's it for today's video. Don't forget to do the practice problems, and I'll see you soon.